Mungi, and today's video is going to go over a review of the stress and strain diagram. As an outline for today, we're going to go over the overview of the stress-strain diagram. I'm going to go over different types of material behaviors. We're going to quickly cover the modulus of resilience and the modulus of toughness, and then I'm going to leave you with a practice problem to try what you learned today on your own. So let's start by drawing out, taking this whole slide to show you how to draw and understand the conventional stress-strain diagram, okay? So by conventional stress-strain diagram, what I mean is for a typical type of loading, and we're just going to do this for normal stress and strain, so sigma and epsilon, okay? We're going to put sigma here on the y-axis, and if you remember, sigma corresponds to the normal stress, and epsilon corresponds to the normal strain, okay? And we have 4 different regions that we're going to cover in a little bit more detail right now. What's happening here, just to actually kind of pull back so we know what we're even drawing, think of a bar, okay? Think of a bar like this. Okay. What we're drawing here is we're drawing a diagram that corresponds to, if we were to pull this bar in tension, what would be the corresponding, remember this is P and this bar has some cross-sectional area, sigma equals P over A, epsilon equals delta L over L, the change in length over the original length, okay? So if we're going to pull with some P, what is the corresponding sigma normal stress and strain as we increase that loading P? And that's what's happening on this diagram. So as we start at 0, what is 0 load? 0 load P corresponds to 0 stress, 0 strain, right? If I had this bar here and I have no force pulling on the bar, it's not going to change in length and it's not going to have any internal stress developing, right? Due to those forces. There are no forces there. The minute I start pulling on the bar, I don't think this Apple Pencil is going to increase. But if this were something that had some elasticity, or I could pull a little bit more with my bare hands, but if this were going to pull at all, the more force I'm going to add, the more internal stress that's developing in the system, and the longer this member is going to become. That is the stress and strain. So the first portion that occurs on the stress-strain diagram is a straight line, okay? This is called our elastic region, okay? I'm going to draw the diagram first, and then we're going to separate this all and go into the different regions. After this system behaves elastically, which means that there's a proportional increase between the stress and strain. After I've reached some limit where this proportional increase between stress and strain can no longer be sustained, I have this portion that we call yielding, where I see elongation in the member. It's getting longer, the strain is increasing, but there's no stress that's developing inside. So we have an increase of strain, but no increase in stress. We call this portion yielding. After we go through yielding, we have the next portion, which is called strain hardening. All of a sudden, we get this increase, but it's no longer linear anymore, okay? It follows a curve. And then we get to this point where the system says, okay, I cannot sustain any more stress. I'm going to break, okay? This is the max stress I can sustain. This is the ultimate stress I can sustain. I am now on my way to failure. I cannot do it anymore. And you get to your failure point, right? It's really similar to internal stress. You can only handle so much, right, until you're going to break. So this is what our stress-strain diagram looks like. Now, I'm going to go ahead and break these up into some sections so we can kind of delve a little deeper in this review. Okay, so we have here section 1. Remember, we called this the elastic region, okay? This elastic region corresponds to elastic behavior, okay? What we see here, we see a linear curve, okay? And the slope of this line is actually E, the modulus of elasticity. That's the slope of this line, right? This line is defined by y equals mx. There's no b because b is 0, or sigma equals E not E sigma, E epsilon, right? That's Y and X. This is Hooke's law. Remember, Hooke's law only applies in the elastic region because that's where it's a straight line. That is a function of a straight line. You cannot apply Hooke's law past the elastic portion. Big no, okay? So, we call this point right here our proportional limit because that is where we stop being proportional. We've reached the limit. Okay, proportional limit. Now, next section here we have is called yielding. And that's what I was telling you, where we see this increase in strain, we see a lengthening of the member, but we see no increase in stress. And this is when the system is going through this point where it's taking the stress, it's not increasing, but it's increasing the length of the member until it can no longer sustain that level of stress, and we see an increase of stress corresponding to an increase of strain. Although it's no longer proportional, it acts along this curve. And we go into the third section, which we call strain hardening. And that is this highlighted orange section here. And what happens during this portion is we then reach the point of ultimate stress, okay? This is really important. I forgot to mention the first point in the yielding section. This is our yield point. This is the point that we use often, corresponding to sigma y of certain types of material, which is the yield stress of that material, okay? The ultimate stress is the max stress that it can withstand before it starts losing that ability to take anything else, and it starts the process going to our failure point. This fourth section of the diagram is called necking. Okay, what does that even mean? Why is it called necking? I want you to think of this kind of tube. Let's say that you're pulling. What happens when you pull something like, think of like taffy, right? That candy, that really stretchy type of candy. You're going to pull taffy. It's going to get longer, and you're going to start seeing the middle get really, 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 really thin. And then all of a sudden, in the very middle, it's going to get so thin, it's going to break there. That's why it's called necking. It's like becoming a little neck, and then it just breaks. Okay, a little tiny portion. That's what's happening there. Okay, now, all of the behavior here is called elastic behavior. Makes sense because that's the elastic region. Everything else, what's it called if it's not elastic? It's plastic. Okay, remember, you can only use Hooke's law. It's only valid in the elastic region. Okay, now let's talk about a few things. Okay, let's talk about a few things about the elastic region. Remember, the elastic region, that's where we have straight line behavior, that proportional relationship between stress and strain. So sigma is proportional to epsilon. Okay, this is called linear elastic. Okay, now one thing we need to remember is that there's no permanent deformation in the elastic region. What does that mean? Means that as long as I pull on this bar and I don't increase the stress to the yield point, it will always bounce back to its original shape. The minute I pull it past the elastic region, it will never go back to its original shape. It'll have something called permanent deformation. Okay, it's like if you're kind of just playing with the taffy, it can kind of be put back to its original length, but if you pull the taffy really, really long, it can never go back to that original length. Okay, so that elastic region, I'm going to put this in a highlight here, corresponds to no permanent deformation. It can bounce back, okay? Now, I want you to think about now the plastic region. That means that there's no more bounce back. The minute you hit the plastic region, you have some permanent deformation there, okay? Now, let's talk about material behavior under stress and strain, okay? We have two different kinds of categories we're going to talk about today. We have ductile materials and brittle materials. So, what is a ductile material? A ductile material means that it can sustain a large amount of strain or deformation before you just kind of hit that fracture point. This stress strain diagram that we drew is for a ductile material, and I'll show you why. We can go through this linear elastic portion, we go through some yielding, we have this nice curve before we get to the ultimate stress, and then we go on our way down before we get to failure. We have a clear warning before we just go to failure, okay? A brittle material does not give you that warning. It goes from you're loading, you're taking the stress, all of a sudden it cracks, okay? You want to think of brittle like a tortilla chip. You can just crack that and there's really no warning that it's going to break. Versus something like that taffy where I can take my sweet time stretching it and it's going to deform and deform and deform and it's going to go through necking and I get to see all of that before it breaks, okay? When you're thinking of designing a system, okay, what do you think would be a better system or better type of material to use, ductile or brittle? Okay, now we do use brittle material sometimes and I'll talk about different kinds of material, but we often want to use ductile materials like steel, okay? They are able to sustain more deformation before they just up and fail on us, okay? So we want to use ductile material more often. Of course, there are cases we do use brittle material a lot. We just have some ways of fixing that so that it gives us a little bit of a warning before it's just going to break on us, okay? Now, we've talked about this already. Ductile materials experience this large deformation before fracture. One of our prime examples is steel, which we use a lot. And basically, they absorb energy because they exhibit these large deformations before they fail. We can measure ductility through something called percent elongation and percent reduction in area. Okay, so let's go ahead and write these two formulas out. Percent elongation is equal to the final length minus the initial length divided by the initial length times 100% because this is a percent. This is around 38% for mild steel, your percent elongation that you're going to get, okay? And our percent reduction in area would be equal to area initial minus area final divided by area initial times 100%. And this is around 60% for mild steel, okay? Now let's move on to talk about brittle materials. So, brittle materials are materials that exhibit no yielding before failure, so we don't get that warning. We don't get that energy absorption and that large deformation, okay? They don't have a well-defined fracture stress, so it just kind of happens all of a sudden. Compared with behavior in tension, brittle materials have high compressive strength, so that means that they're really good in the axial direction when we're compressing like this, okay? They have tension failure of brittle materials, which is very quick, but compression failure is a little bit better. So one of the most common types of brittle materials that we use is concrete. It has a high capacity for compression, but it has a low capacity for tension. So what do we do to fix the low capacity for tension? We reinforce concrete. That's why we build our systems with reinforced concrete. We reinforce it with steel, a ductile material that helps with tension. Okay. Modulus of elasticity, we already talked about. This is the slope of your stress strain diagram. And remember, this can only be used for linear elastic behavior. We have two things that I want to cover last. Modulus of resilience. I've put the formula for the modulus of resilience here for you. But basically, when the stress reaches the proportional limit, the strain energy density is called the modulus of resilience. Why is this important? It's particularly important when we're designing something like bumpers or shock absorbers to take in that energy, and this is equal to the area under the shaded region of your stress strain diagram. Or you can use this formula here. Last one is modulus of toughness. This is the area under the entire stress strain diagram. And why is this important? This is important when we're designing members that could be accidentally overloaded. So if you're designing a member like this, it is important to know what your modulus of toughness is. Now, I have put here a practice problem for you to go ahead. You can try putting this on Excel. You can graph this yourself and see if you get it. And you can answer the following practice problems to make sure that you understand all of the elements that we went over today in this video.